survive. And of course, in computer science, there are countless optimization problems that you can use game theory for. So what you will learn here will not only be useful for synthesis. Maybe in your career later you will say, this problem can actually nicely be modeled as a game, and then I can use what I have learned in this lecture to solve it. Okay, so this was some general introduction into games. Now we will look at very specific kinds of games, namely games on graphs. These games on graphs are defined by two components. We have a graph and a winning condition on this graph. The graph is actually defined in a quite standard way. We have some initial state which we call Q0, where everything starts. Then we have a certain set of states in the graph, and we have a certain set of edges between these states in the graph. The edges, they are all directed, so they have a dedicated source and a dedicated destination. And one additional rule that we have for our game graphs is that every state has at least one outgoing edge. This is written here as a complicated formula saying that every state in our set of states, there exists some other state or the same state such that we have an edge from Q to Q prime. So this pair Q, Q prime is element of our set of edges, our set of state transitions. There is one special thing about our game graphs, namely the set of states is partitioned into two sets of states, which we call Q0 and Q1. Every state is either a Q0 state or a Q1 state. And the reason for this is that our game will be played by two players, which we call player 0 and player 1. And the game is played in the following way. Whenever we are currently in a state that belongs to the set Q0, then player 0 gets to pick one of the successor states. And whenever we are in a state that belongs to player 1, then player 1 picks a successor state. And this is repeated basically in an infinite execution. So the plays that we play on this game graph, they are not finite, they are infinite, at least conceptually. Here is an example just to illustrate how these graphs look like. Here I try to define it formally just by listing the set of states and listing all edges in this game graph, but usually we visualize such a game graph in this way. States that belong to Q0, so to player 0, we usually visualize as a circle. This is easy to remember because the 0 in player 0 looks like a circle. And intuitively, we always look at the game from the perspective of player 0. So we are always player 0, and player 1, his states are visualized with a box, and player 1 is always the evil guy who wants to prevent us from reaching our goal, from winning the game. So how is this game played? The initial state Q0, we sometimes mark it with an incoming error that comes from nowhere. This state is a box state, so it belongs to Q1, so to player 1. So let's say I'm player 1, so I can choose a successor. I can choose either to go to Q1 or to Q3. Let's say I pick Q3 because then I can pick the successor again. When I'm in Q3, I can decide between 1 and 2. In both cases, you will have to pick a successor. So let's say I decide that we go here. Now it's your turn to pick a successor, which can either be Q5 or Q2. And this is repeated basically in an infinite execution. So this is how these games on graphs basically look like and work. We can model many real-world games as such games on graphs. Here I try to sketch how we could model tic-tac-toe as such a game on a graph. Basically, the states are just the different configurations of our grid. Our initial state should have an incoming error here. Represents the empty grid, and I said that player 1 places the cross tokens. So the initial state is a player 1 state where the player 1 has 8 different possibilities to pick one of the successor states, and each of these successor states basically correspond to one of the choice for placing the cross in a certain empty grid. Then all the successor states are player 0 states, which means that from here the circle player can choose a successor state, and each of these states again has 8 successors, namely the 8 different possibilities where the circle can be placed, and so on. So this way we can construct a rather large graph which represents the tic-tac-toe game. Some states will have the winning condition satisfied. At this point we can stop constructing this game graph basically. Now, tricky question to you, is this a game graph according to our definition from before?
No, because there are leaf nodes, like
yes.
If everything's full, there are no outgoing nodes.
Exactly. Initially I said that every state must have at least one successor. The reason for this is that our games are actually infinite. We continue, continue, continue. But if there are states like this which do not have any outgoing edges, then we cannot play an infinite game on this game graph. But there is actually an easy way to fix this. We can just add self-loops. This way we can go on forever, but nothing changes anymore. So going from a finite to an infinite game is always easily possible. So this was how we can model tic-tac-toe as a graph game. Initially I also said that a game consists of 2 parts. First we have a graph, which basically kind of defines the rules for the game. And second, we also have a winning condition defined on this graph. Now there are different kinds of winning conditions that we can have on such a graph. Usually these winning conditions are defined via a certain set of states. And a winning condition may be, for instance, to reach a certain set of states at least once. So with this winning condition, the player 0 would win the game if the play at some point reaches this set of states F. Otherwise, if this set of states F is never reached, then player 0 loses and player 1 wins. Another typical winning condition is to have a certain set of states that needs to be reset not only once, but infinitely often. Yet another winning condition would be we have a certain region of states and we must never leave this region of states. If we ever leave this region of states, then we have lost the game. So there are many different winning conditions. In this lecture we will not talk about them in a lot of detail. This will be more or less the content of the next lecture, where we will go over different kinds of winning conditions and learn an algorithm to compute a strategy for these different kinds of winning conditions. Okay, so this was how game graphs are defined. The next thing I would like to discuss with you is MuCalculus. As I already mentioned in the beginning, MuCalculus is kind of math applied to game graphs, and we will use this math later in the next lecture to solve games. For now, this math may look, I don't know, completely useless to you, but next lecture you will see that it is actually useful for solving this game. MuCalculus is actually basically formulas that we can write over game graphs. We can define a formal syntax and the semantics for these formulas, but I do not want to do this. I would rather like to introduce MuCalculus to you by example. Later I also have slides that present the formal syntax and semantics, but we will only go over them briefly. The more important thing here is that you get the intuitive meaning of these formulas. So MuCalculus is formulas over a game graph, and intuitively these formulas always evaluate to a certain set of states in this game graph. So the result of evaluating such a formula is always a certain set of states in the graph. As an example, we can use in MuCalculus formulas all the usual set operations you're used to. So set union, set intersection, or set subtraction. So this would be a MuCalculus formula for a certain game graph. Let's say our game graph has 7 different states called Q1 to Q7, And we also have a certain set of states which is named S1, consisting only of state 2, 4, and 5. Then the intuitive meaning of this mu-calculus formula should not be too difficult. Maybe you can think of it a second and try to figure out what is the meaning of this mu-calculus formula. It's just a set of states. Feel free to write down intermediate results.
You want to know the class area?
Yes. So what I would like you to do is try to figure out what could be the meaning of this formula. Formulas always evaluate to a certain set of states. So the meaning of this formula, the result of this formula is just a certain set of states.
Q1, Q4, and Q5.
1, 4, 5. Yes, I think so. So the meaning of this formula is just take the set of all states containing only the state Q1, build the union with all states in S1, which would be 1, 2, 4, 5. So this part has the meaning 1, 2, 4, 5. Now we intersect it with all states except for Q2. So the overall result would be 1, 2 not, because 2 is cut away by this part, 4, 5. So 1, 4, 5 would be the result of this formula. So basically these set operations just have the usual meaning in our mu-calculus formulas. What we can also have in mu-calculus formulas are functions. Such a function takes as an argument a certain set of states. I write this here as 2 to the power of q. I'm not sure if you're familiar with this notation, but 2 to the power of a certain set is always the power set of this set. So the set of all subsets of the set. So 2 to the power of q means all subsets of q. So the empty set, the set only consisting of q0 and so on, up to the set of all states. So intuitively, a function takes a set of states and returns a set of states, and we can also use such functions in mu-calculus formulas. The next thing we allow in such mu-calculus formulas are least fixed point operators, which we write with a mu. A mu-calculus formula containing a least fixed point always looks like this. We have this mu, indicating that this is a least fixed point. Then we have a certain variable, which is named x here, and this variable also represents a certain set of states. And then we have some mu-calculus formula in which this variable x appears somewhere. So this is how you write mu-calculus formulas with such a least fixed point operator. The question is now, what is the meaning of this strange least fixed point operator? And for that, I would like to do a small excursion to you to the world of fixed points. Let's say we have some arbitrary domain D of elements, and we have a function, f, which takes elements of D and produces elements of the domain D as a result. Then, a fixed point of this function f is simply some element x, such that f of x is again x. So if you apply f to some element and you get back the same element, then this element is a fixed point of the function. This is just the intuitive meaning of what a fixed point is. Here is an example. Let's say our domain is just a set of natural numbers, and our function f is defined in the following way. It takes the argument x, adds 10, divides by 2, and then rounds down to the next integer number. Now, question to you. Find a fixed point for this function.
10.
So, sorry?
10.
10. Let's see. 10, oopsie. 10 plus 10 is 20, divided by 2 is 10, rounded down is 10 again, so f of 10 is 10, so 10 is a fixed point, yes. Actually, I found a different one. 9 also works, I think. 9 plus 10 is 19, divided by 2 is 9.5, but rounded down is 9 again. So f of 9 is also 9. In general, what we can do is just write down, try to evaluate the function for different values and then just pick these entries where the argument is the result, basically. Here is also a graphical illustration. The red line represents f of x and the blue line represents x, and the fixed points are exactly these points where f of x is equal to x, which is not, I think there is a off by 1 on the scale, but you get the idea. So this is what fixed points are. The question is now, how can we compute such fixed points? I would say this is quite difficult in general, depending on how our formula f looks like. But independent of how our formula f looks like, we can compute such fixed points quite easily by just evaluating the function f for different values of x. And this we can do in a quite straightforward way if two assumptions are satisfied. The first assumption is that our domain of elements is finite. So the set of natural numbers would not work, but any finite domain would work. And the second assumption that we impose is that our function f is monotonic. Intuitively, this just means if we put in a larger value, then we can only get out a larger value. If we put in a larger value, we cannot get out a smaller value, basically. So the function f only increases, it doesn't decrease. With these two assumptions, we can define a very, very simple algorithm to compute fixed points. And this algorithm works as follows. We start with the smallest element in our domain, whatever that means, and then as long as this value x changes, we just compute the new value of x by applying f to our old value of x. Let's try this out. Do I have it on the slides? Yes. If this really works for our example. Question, yes?
I think I could use the big O notation to prove that it's not possible to find a fixed point.
Okay, how would you do that?
I would say if the growth of the function is too steep, it's impossible that there's any fixed point coming eventually.
Yes, that's a good point. So let's postpone this example a little bit and think about the correctness of this algorithm. You are saying that maybe there is no fixed point because maybe our function looks like this. X, this is basically also x, and maybe our f of x looks like this. In this case, we would not find a fixed point with this algorithm is your argument, basically, as I got it, because you say, okay, I start with 0. If it looks like this, then we already have a fixed point at the value 0, but let's say your function looks like this. So we start, this is basically f of 0. I take f of 0 here. This is f of 0, which would be here, and so on, and so on, and it gets bigger and bigger and bigger, and we never find a fixed point, is your argument, basically, right? But now I'm saying that, well, our domain is finite. So this function cannot grow forever. There is basically some largest element. And at some point we must hit this largest element and then it cannot get bigger anymore. So in the worst case, simply the largest element in our domain would be the least fixed point. Any other reasons why this algorithm could not work, or any arguments why it should work? Let's split a correctness argument for this algorithm in two parts. First part is, if it terminates, it produces a fixed point. Can we find some explanation why this is the case? So if this algorithm terminates, it will return a fixed point. That's my claim. Why?
Yeah, if there's a maximum element, then at some point it would not change anymore. So the while loop would finish, and
you are already given an argument why it terminates, but I was just asking if it terminates, just assume that it terminates, will it return a fixed point or some garbage?
I think it doesn't have to return a fixed point, because I take the example you've drawn here, and we take a finite domain. The functions, they don't have to cross just because it's finite. So in
Yes.
worst case we have it terminates, but we have no fixed point.
Yeah, but then I also say that our function is monotonic, so it can only go up, 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 and it cannot go down again. So here it would go this way. Use a different color.
Ah, okay.
There cannot be any larger element anymore, but there must be some element, so the only possibility is that it goes here. And then, so this is where the domain ends. In the worst case, we would cross it here.
but if f of x is not getting bigger, but it's getting smaller, so if x is getting bigger, but f of x is getting smaller, two won't meet.
Yes, but actually my assumption says that it will only get bigger.
Okay.
Okay, so you just gave the answer.
Actually,
It returns, in worst case, it returns the last point as a fixed point.
Yes, but the answer I was actually aiming for, I was just asking if it terminates, will it be a fixed point? And the answer would be yes, because the termination condition is actually exactly that we have reached a fixed point, because if x doesn't change anymore, then this means that x has to be equal to f of x. This is exactly what I meant by writing here x. As long as x changes, we keep repeating. So if we stop repeating, then this just means that f is equal to f of x. So if it terminates, then it will produce a fixed point. This is quite easy to see even without these assumptions, because this loop terminates exactly if x is equal to f of x. So if it terminates, we have our fixed point. The more difficult question you are already thinking about is, does it always terminate? And for that, you already gave a solution, yes, because f is monotonic, so the elements can only get bigger, 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 and the domain is finite, so at some point they cannot grow anymore, so there can only be a finite number of getting bigger before we hit either a fixed point or the biggest element in our domain. So this is the intuitive reason why this algorithm works. Now I would suggest that we simply take a break, as usual, of 15 minutes. Maybe don't just run away. Georg would also like to briefly hand back your homeworks and maybe briefly discuss it with you, or just say,
yeah,
okay,
one thing.